A developer can write an AI script and spin up a working demo in a few hours. Yet, getting that same model deployed across a large corporation often takes months or stalls indefinitely. This gap is known as pilot purgatory. On the left, we have a fast, functional proof of concept built in a technical sandbox. On the right, the polished, production-ready interface where that model belongs. Between them is a wall that most projects never cross. Engineering teams often mistake a stalled project for a coding problem. In reality, the project usually halts because the team cannot demonstrate a clear financial return to the CFO. Many other projects fail simply because they cannot satisfy the organization's security and data compliance mandates. Moving an AI system from a local sandbox into enterprise production requires a framework that bridges technical capability with business logic. Transitioning a model to production is an architectural and governance challenge. The math is only the starting point. To understand this transition, we are reverse engineering an AI-powered medical insurance appeals engine. Currently, human medical billing teams spend 45 minutes manually drafting a single appeal for a denied insurance claim. A human agent must read the patient's clinical chart, identify the insurer's specific denial code, cross-reference that code with the relevant clause in a massive policy guide, and finally write a formal appeal letter. This bottleneck delays patient care and traps millions of dollars in uncollected revenue for hospital systems. A fully operational AI system can now execute this entire workflow while maintaining strict adherence to federal HIPAA regulations. By starting with this finished system and working backward, we can map the exact anatomy of a successful enterprise deployment. We begin at the end of the pipeline, where the final output meets the professional user. Corporate governance requires that automated systems avoid making final, autonomous decisions that impact a human being's financial or physical health. Architects satisfy this requirement by implementing a human-in-the-loop workflow. In this case study, the AI drafts the appeal letter and places it in a secure queue. The document remains there until a human medical coder reviews the citations and clicks Approve. These ethical guardrails are intentional, structural friction points. They protect the organization from the legal liabilities of autonomous error. Moving backward from the user dashboard, we reach the model deployment and hosting layer. An organization's data tiering policy dictates what information can enter specific AI environments. Patient medical charts are classified as red data, ultra-sensitive information that carries severe regulatory penalties if exposed. Handling red data strictly forbids public AI APIs. They are crossed out entirely. Instead, the hospital hosts a frontier open weights model within a private virtual private cloud. Here, a masking tool intercepts documents, stripping away identifiers like social security numbers before text enters the model. On the output side, an automated checker compares the generated appeal against the original chart to ensure the medical facts remain accurate and free of hallucinations. Clear data tiering and isolated infrastructure allow an organization to deploy a viable enterprise tool without creating a compliance liability. Zooming into the core processing layer, we can see why a standard Retrieval Augmented Generation, or RAG, architecture was insufficient. Standard RAG retrieves text based on semantic similarity, which makes it difficult to connect disparate facts across massive files in different formats. This diagram displays our core notes. A medical appeal requires linking a doctor's clinical note to a specific legal clause in an insurer's PDF. The solution is a multi-agent system operating on a graph RAG foundation. First, the parser agent ingests the XML file and extracts the denial code. Next, the researcher agent uses graph RAG to map charts against policy codebooks, pinpointing the exact medical proof required to refute that denial code. Finally, the writer agent takes those findings and drafts the formal appeal letter, including precise citations from the files located by the researcher. Chaining specialized agents over a graph network replicates the multi-step reasoning a human expert uses when navigating complex documents. Beyond technical design, we must address the financial reality. Building and running this multi-agent system requires significant capital investment. This AI efficiency formula mathematically justifies the deployment to the CFO. Hard ROI is the direct reduction of costs achieved through model cascading, prompt caching, or eliminating expensive software seat licenses. In this case, a manual process costing $25,000 a month in labor is reduced to $4,250 a month, including the costs of API tokens and human review time. Soft ROI accounts for velocity and capacity gains. This allows the existing staff to handle 10 times the workload or focus on complex edge cases without increasing headcount. CFOs approve technology that serves as a mathematically proven efficiency multiplier. This table outlines the holistic structure of the medical appeals system we just deconstructed. It is the Enterprise AI Blueprint, a framework for designing and pitching comprehensive solutions. A complete blueprint aligns the manual bottleneck, the required raw data, the technical architecture, the deployment environment, and the ethical risk loops. The utility of AI stems from the alignment of engineering with human and business objectives. Using this comprehensive framework allows a developer to successfully bridge the gap between technical design and executive implementation. Your objective is to find the most expensive manual bottleneck in your organization, define the data requirements, and architect the solution.